Hey everybody, just made it through our first week. So, there are three kinds of lies. Lies, damned lies, and statistics. I just quoted Mark Twain, who was describing the persuasive power of numbers, particularly the use of statistics. These use of statistics have been used to weaken arguments throughout the ages. It is also sometimes used to doubt statistical reasoning when arguing with an opponent by simply saying statistics are just lies anyway. And that is the topic of today's video, statistics. Statistics is the analysis and interpretation of data. As I mentioned earlier, data and numbers, they don't have agendas, feelings, they don't even what you think. They're just data. However, the analysis and interpretation of data is performed by humans, and as we all know,
humans are prone to error.
In the 1950s, journalist Darrell Huff wrote a book called How to Lie with Statistics. He wasn't being malicious, he was just exposing ways that people manipulate you with bad data. Examples of tips he would suggest was making sure data samples are randomly selected, ensuring that graphs are written so that they don't distort the viewer's interpretation to make a misinterpreted conclusion, and finally, also reminding us of that famous line that I've said in class many times:
Correlation does not mean causation.
Although sometimes it does. Regardless, statistics help us make decisions, understand trends in the world. The current rate of coronavirus, as seen in this graph made on March 18, 2020, shows us an exponential growth curve. So 2 weeks ago, when we were all business as usual, it was in its lagging growth stage. Eventually, businesses, local, state, and finally, federal governments have realized that to slow the exponential spread, we had to shut things down. As much as this seems like an overreaction, that chart would rise much faster without social distancing measures. In this video, we will go over some basic statistics such as mean, median, and mode, as well as perform an example statistical analysis called a chi-square. Please have a calculator ready, and let's get started. Statistics, the analysis and interpretation of data. So some of the simplest statistics out there are what we call the 3 M's: mean, median, and mode. Mean is an average of all the data in a set. Median is the middle number in a set of data, once you put all of the numbers in numerical order. Mode is the most frequent data in a set. So the example I'm going to use, let's say you have a class and everybody's shoe sizes have been given. So what you would do to find your mean is you would add up every shoe size and then divide it by, in this case, 24. And you find out that the mean shoe size for this class is 7.9 or 8. So in other words, the average shoe size is about 8 for this particular class. The median shoe size is also 8. Now, in order to find median, you need to make sure all of your numbers are placed in numerical order, and you simply just find the numbers found in the middle. Since this is an even set of data with 24 pieces of data in it, you're going to go to the very middle, and since both numbers are 8, our median shoe size is 8. Let's say that it was 7 and 8. What you would do is you would take these two numbers, add it together, and divide by 2. And so if this were the case, it would end up being 7.5. The mode, again, is the most frequent data in a number set. And as you can see, 7 shows up more frequently than any other set in this data. And so here's some really simple statistics that we can use from a simple set of data. But you got to be careful when using mean, median, and mode. Means, for example, can be affected by outliers. So here is a list of people and the amount of calories that they consume per day. And if you take a look down the line, it seems fairly steady until you get down to this individual here named Samus. Yes, I am a Metroid fan, and I cannot wait for Metroid Prime 4 to come out on Nintendo Switch. So an outlier is a data point that deviates heavily from the rest of the data. So Samus eats way more food than normal. And that's because Samus is an athlete. So athletes have to eat more food than the average person. So the problem with outliers is that they do not seem to represent the data in a particular set. So when we look at the overall mean, it's 2,233.8 calories. But the mean with Samus removed is then reduced down to 1,926.4 calories, which makes it more realistic for this data set. The advantage of a median, it is not affected by outliers. All right. The problem is they may not account for all observations in a given data set. So for example, let's say that you have a lot of people that eat very few calories, and then you have quite a few that eat a lot of calories. So your median number may seem smaller or larger than the mean in that case. It is possible to have multiple modes in this data set. So 1,985 and 2,000 are the two different modes that exist within this particular area. Other simple forms of statistics that you can perform on data include ranges, minimums, and maximums. So we're going to apply that same data set from the previous slide. A minimum is just the smallest number in a data set. A maximum is the largest number in a data set. And a range is just the difference between the maximum and the minimum. So the bigger difference in your range, the more variability you have in your data set. So going back to this data set from before, Katniss only consumes 1,250 calories a day. Samus consumes 5,000 calories a day. So if we were to include the original data set range, that's 3,750 calories is the range between all members of that group. But if we take Samus out, it only ends up being 1,050 calories. And so you've got to be careful because just like means, ranges can be drastically large and unrepresentative of a data set if there are outliers. And I think it's very important to understand outliers because especially in the business world, when they say the average customer saves, it just so happens that one lucky person saved a lot of money and everybody else saved a nominal amount. And so it makes it look like the overall savings is higher than it actually is. So I would always ask for a median as well as a mean when trying to find out information like that. I want to briefly touch on statistical correlations. We have talked about this previously in class, but a correlation in statistics is a measure of the direction and strength of a linear association. So oftentimes they're depicted as scatter plots, and the scatter plots will use what's called a trend line. That's this blue line right here. And the closer the dots are to the trend line, the stronger the correlation is. Now, if the correlation is going upwards, it's positive. If it's going downwards, it's negative. The farther away the dots are, the less of a correlation that there is. And then sometimes dots are all over the place, and that just indicates there is no correlation. But please don't forget, as I've said in class and Mark Twain earlier, correlation does not mean causation. Now, sometimes it does, but in this particular graph, the divorce rate in Maine correlates with the per capita consumption of margarine. So in other words, the more margarine that is consumed, the more divorces occur. The less margarine consumed, the less divorces occur. Well, I think we all know that that has nothing to do with it, unless that was the main reason why your marriage failed, because you couldn't agree upon margarine or butter. I now want to move on to a particular statistical analysis that I want you all to learn in this class, and it falls under a class of statistical analysis called a hypothesis test. So hypothesis testing is used to test the statistical significance of the data collected when compared to a baseline. So when using statistics in an experiment, oftentimes the experimenter wants to test the validity of their claim or give it some form of statistical significance. So statistical significance means that the trend in data was not due to chance alone, but it was actually due to a variable that is tested. Statistical significance is used to help scientists tell if the trends in data occur due to the variables they test or if it was just random chance that caused that particular trend. So this is important because while we might be able to eyeball the data and come to a conclusion, statistics takes out our subjective interpretation and determines if our data behave based on a variable we added or if our data was subject to random chance. To do this, an experimenter will develop two hypotheses. One is called the null hypothesis. The null hypothesis states that the baseline data is equal to the claim value. In other words, the null hypothesis always states that the parameter to be tested, no matter what, will remain the same, and there will be no difference in any of the different independent variables in a particular group. Then you have an alternative hypothesis, which states that the baseline data is not equal to the claimed value. So in other words, there is a particular group within your independent variable that actually is operating much higher than, say, other groups tested. So, for example, if you want to test the effects of different cold medications and how they treat the cold, I would set up a hypothesis such as this. So what I've got here is an experimental setup where we're going to test how well people respond to particular cold medications in the event that they have a cold. So a team of pharmaceutical researchers are interested to know if one particular over-the-counter treatment treats the symptoms of a cold better than another. So thus far, no clinical research claims that one drug works better than the other. So this is what we call baseline information. So what we have from previous studies show us that one drug does not seem to work better overall on people than the other. So this is what would be known as our null hypothesis. We would say that there is no difference in the treatment of symptoms of the patients with any of the cold medications. The alternative hypothesis, however, we would say that some cold medications seem to treat symptoms better than others. So in other words, the null hypothesis states that if there is a difference in how patients respond to certain medications, it's not significant enough to claim one medication does better than the other. It was just happened to be the sample we tested. It was just chance. Likewise, the alternative hypothesis states that some medications will show a significant difference in performance amongst the patients tested. Hypothesis testing can be carried out by many different types of tests, but I've chosen a simple type of hypothesis testing called Chisquare Analysis. Chisquare Analysis. And of course, you'll see the equation up here in the upper right section of the corner of this slideshow. Please do not be intimidated. It is very easy to do once you've learned how to do it. So let's apply hypothesis testing and statistical significance in an experiment concerning cold medications, and in more detail using the Chisquare analysis. So again, if you remember, we're trying to figure out if patients respond better to particular types of medications. The Chisquare analysis compares the deviation between observed data and expected data. The greater the deviation, the more likely that the observed data show a difference in treatments. In other words, the greater the deviation between observed data. So observed data is, in our case, would be how many patients responded best to a particular medication. And so right here I have 5: Tylenol, cold and sinus, Sudafed, Vicks, Alka-Seltzer, and Bob's all-natural cold medication. So these would be the number of patients that said this medication did best for this particular experiment. Now, expected patients. Expected is always going to be based on your null hypothesis. And if you remember, the null hypothesis would say that there will be no difference in how patients are affected by these medications. And so your expected patients treated is essentially this number divided by categories. So in other words, we would say that if this is all about the same, then we should expect about 200 people in each category to show us that these treatments are all pretty much the same in how they affect people. So to get started, you just plug these numbers in. You take 297 for the observed minus 200 for the expected, and you end up with 97. When you square 97, the number becomes 9,409. You take that number, divide it by 200. And so your chi-square for that particular one, Tylenol, cold and sinus, is 47.04. You do this for every category, and then at the very end, you add all of the categories together, and this adds all together to be your total chi-square. So what does this number mean? The point of this number is we're trying to determine whether or not any one of those drugs work better than each other, or if it just so happens that there really is no difference. Everybody seems to react fairly similarly to each one of those drugs. So we have our total chi-square, which is 531.76. And what we're going to do is we're going to match it up against a table called critical values of chi-square. Now, this table was developed by statisticians. I promise you, I don't even know how they got these numbers. But it is a constant number used amongst anybody who uses the chi-square analysis. So here's how do we interpret this table. We first have to determine what is our degrees of freedom. Degrees of freedom essentially are how many categories do we have of variability. In other words, we have 5 distinctive categories that we're testing. But degrees of freedom always is the number of categories minus 1. So n is the number of categories that are used. So in this case, our degrees of freedom is 4. So we're only going to focus on this row right here. The next thing is you want to be able to determine statistical significance. Generally speaking, this is what this is right here, 0.05, 0.01. The lower the significance, the stronger the data are going to be if the alternative hypothesis is in fact true. The way we interpret this is that there is a 95% chance that some of those medications actually work better than others. If you say 0.01, there's a 99% chance that there are some statistical significant difference in the way these patients are affected by these medications. So the way we do this is we're going to head down to here, and most scientists use the 0.05 column, but I'm going to go with the 0.01 because we're dealing with medicine, something very important in life and death issues. And so what we're going to do is we're going to look at these two numbers right here. 9.49 and 13.28. Our chi-square value is 531.76. So what do? You compare the numbers against each other. If your total chi-square is less than or equal to the tables, the null hypothesis is true. In other words, if our number ended up being 8.25, then we would say that there's no difference in how patients react to these medications. But our total chi-square is more than these particular numbers, so therefore we can conclude that our chi-square we can conclude that there are some medications that work better than others. Now, I do realize you can eyeball that and say, oh, yeah, definitely. People tend to respond better to Sudafed first and then Tylenol cold and sinus. But we have to do another chi-square analysis to see if there's a statistical significant difference just within these 3 right here. But we can certainly rule out that Alka-Seltzer and Bob's all-natural cold medication in this example, and please remember this is fictional, but we would say in this example that Alka-Seltzer and Bob's all-natural cold medication do not seem to work. Now that you learned some basic statistics and how to perform a chi-square test, be sure to go to the Statistics and Graphing file in Class Topics and locate the Practice Chi-Square problems. Do these to prepare for your quiz over statistics and graphing.